Kia ora. We're going to look at some integration problems today. One of the frustrating things about integration is that there seem to be so many different things you could possibly do to solve integration problems. But one of the most important ones to understand is integration by parts. A lot of the other ones maybe you won't end up doing very often, but parts is particularly important that we understand. So we're going to do a couple of integration by parts problems and also a trig substitution and just sort of see how that all works. All right, so with parts, we have this formula. This may be how it was presented to you, where it basically tells you the integral of some function times g prime times another thing is equal to fg minus integral of f prime g dx. Now the important thing to look out for here is look at the f's first. You've got f here again, and then f prime. So this f only gets differentiated. So if there's something in your problem that looks like it wants to be differentiated and will be easier to deal with that way, especially as inside this integral here it only involves f prime, then that's a good candidate for choosing for f. Likewise g, we start off with g prime, but on the right hand side we only use g's, so the thing that's g prime is going to be integrated. So let's look at this first problem, integral of log x over x squared dx. The thing that we like to differentiate here is the natural log, because we know that'll turn it into a 1 over x. So if we were to approach a problem like this one by parts, my parts will be first log x. So I'm going to say let f equal log x, and I'll let g prime be whatever's left, 1 over x squared. And then I'm going to need f prime and g as well, so I'll also figure those out. So f prime of x will be 1 over x, and g will be the integral of that. So x to the minus 2 goes to x to the minus 1 with the negative signs. That means my g of x will be negative 1 over x. So now you can see that my integral overall is going to be f times g, so negative log x over x, minus the integral of f prime times g, which is negative 1 over x as well, dx. And you can see that now that's an integral that looks a lot easier to do. So that's going to be negative log x over x. Negative signs will cancel off, so it'll be a plus integral of 1 over x squared dx, and that tells me that I'm going to have negative log x over x minus 1 over x plus our constant of integration. Okay, so typically it's always going to be the case that when you see a log, that's going to be the thing that you want to put into your f if you're going to be using parts, because log differentiates to 1 over x, and 1 over x behaves a lot more nicely in integration. All right, let's do another problem. So we'll do one now with some trigonometry involved. So this next problem is going to be the integral of tan inverse or arctan of 2x dx. You can solve this kind of problem by integration by parts as well. What might look a bit odd about it, however, is that there only appears to be one part. So let's just quickly put the parts formula again. Remember the parts formula says the integral of f times g prime dx is equal to fg minus the integral of f prime g dx. Okay, so when you've got a problem like this one, and it often happens if you have like a standalone logarithm as well, we'll just say that the tan inverse is going to be our f. So we'll say let f be the tan inverse of 2x, and our g prime, now that's just going to be 1, because f times g prime, tan inverse 2x times 1 is just the thing that's inside the integral. And also don't forget that tan inverse of 2x is a thing that we know how to differentiate. So remember the derivative of tan inverse of x is 1 over 1 plus x squared. So if we go and complete the things we need for our parts formula, f prime is going to be 1 over 1 plus 2x squared, all times 2 by the chain rule. So that will be 2 over 1 plus 4x squared. and this will give me g equals x. Therefore, our integral is going to equal f times g, so x times tan inverse of 2x, minus the integral of f prime g, 2x over 1 plus 4x squared dx. All right, now we're not done yet. To solve this one, we need to do a substitution. So let's, you can see that on the bottom of our fraction here, we've got a 1 plus x squared, 4x squared, and the derivative of x squared, well, that piece, is going to be basically a constant times x, or 8x. And I can see a constant times x multiplying my overall expression. So this suggests to me a substitution, which would be u equals 1 plus 4x squared, just to do that integration. And this will tell me that du dx will be 8x, which means that dx will be 1 over 8x times du. So let's go ahead and apply that substitution. So the first part, this part of the integral is already done, so it can just come along for the ride for free. Minus integral of, well, let's see, we're going to have 2x over u times 1 over 8x times du, and you expect that these x's are going to cancel off. If you've done your substitution correctly, that should pretty much always happen. So that'll be x tan inverse x minus the integral, 2 over 8 is a quarter, I'll just stick that at the front, quarter of integral of 1 over u du, which equals, we'll just keep on going. Okay, let's just move across so we can keep it all on the same screen. That's going to equal x tan inverse, so this goes from here up to here, x tan inverse of 2x minus 1 quarter log absolute value of u plus c. And then to finish the problem off, we've done our substitution, we've integrated it, integral of 1 over u is natural log, and then finally we just need to make sure it's all back in terms of x. It's going to be x tan inverse of 2x minus 1 quarter log the absolute value of u. Now u was 1 plus 4x squared, which is always positive, and so it's going to be log of 1 plus 4x squared plus c. And we're finished. Okay, so that's a couple of integration by parts examples. Typically, the thing you want to differentiate will be something that either goes away, like a polynomial getting smaller, like an x squared goes into an x, and if you do it again, it goes into a constant. But if you've got like a log or something like that, that's pretty much always going to be your first port of call. If you have a look through Stuart, he goes through sort of an acronym of ways you might choose this, but easiest way to get comfortable with it is just to work some examples out. Right, we're going to do one more problem. This time we're going to do something a little bit different. We're going to do a trig substitution. So here I've got an integral 0 to 3. Now this is actually one that we do know how to do without doing a trig substitution, but we'll show you how this works with a trig substitution, and then you'll be armed to be able to do this kind of question in a different way when you can't do an alternative technique. So here I've got the integral, it's a definite integral from 0 to 3 of x over the square root of 36 minus x squared dx. Right, so trig substitution, one of the things that should trigger you to look out for these is when you see a square root with an x squared and a number. Now, one of them, it could be a number minus x squared, or x squared minus a number, or x squared plus a number, and depending on which one of these it is, that will help you decide which substitution to make. And so kind of what underlies what we're going to be doing here is these trig identities. So you're hopefully happy with the idea that sine squared theta plus cosine squared theta is equal to 1. And if you divide that one through by cosine squared theta, then that gives you a slightly different one. So if I just go divided by cos squared, divided by cos squared, divided by cos squared, that gives us a different identity, which is well, sine squared over cosine squared is tan squared theta plus 1 equals sec squared theta. All right. And what we want to do is we want to replace the x squared inside here with, in this case, 6 times sine theta, cosine theta, or sec theta, or tan theta, one of those things that's going to make this 36 minus x squared turn into just a standalone term. So I'll show you how this works. So we have number minus x squared. My first trig formula, this one here, that can be rearranged into number minus x squared as well by going cos squared theta equals 1 minus sine squared theta. So what I'm going to do is I'm going to try and make my x squared here look like this sine squared theta term. Now the only other difference here is there's a 36 along for the ride, so I'm going to have to put a number in front of my sine theta as well to make sure that it all matches. So to do this with a trig substitution, I'd say let x equal 6 sine theta. Okay, and then we'll have some various consequences of that to process, but in particular we're going to have that dx will therefore be 6 times cosine theta, sine differentiates to cosine, d theta. So we'll need to put that in with our substitution as well. Also, when x equals 0, we have 6 sine theta equals 0, which implies that theta also equals 0. This is for my limits of integration because I need to turn them into thetas as well. And when x equals 3, we have 6 sine theta equals 3, which means sine theta equals 1/2, which means theta equals, now remember our special triangle, this is the one with the half in it, is this one here where we've got 1, 2, and root 3, and that is 30 degrees. So sine theta equals 1/2, opposite over hypotenuse. That means theta is 30 degrees, which is pi over 6 radians. So let's put all that in and make our new integral. So that equals the integral from theta equals 0 to pi over 6 of x, well x is 6 sine theta, right, divided by the square root of 36 minus x squared, 36 sine squared theta, and then dx. And dx we decided was times 6 cos theta d theta. Okay, so this equals the integral from theta equals 0 to pi over 6. Now 36 minus 36 sine squared theta, let's just do a little bit of scratch working over here, equals 36 times 1 minus sine squared theta, which equals 36 cos squared theta. So this equals 6 sine theta over the square root of 36 cosine squared theta, and that's all times 6 cosine theta d theta. Now, slight problem here. We know that square roots introduce absolute values when we take the square root of something squared. Now, the little piece of information that I forgot to insert here is when we do the substitution, it's important that our substitution is invertible, which means if you think about the sine curve, so here it is, here's our graph of sine. Basically, we're going to restrict ourselves to this part of the sine graph. Okay, so this, what I should have said was negative pi over 2 is less than or equal to theta less than or equal to pi over 2. So that is how that relates to the relationship between our x and our theta. So that means that if we look at cosine theta in the same region, that looks like this. And so it's always going to be positive, which means that my square root is going to give me 6 cosine theta. So that equals the integral from 0 to pi over 6 of 6, let's combine all together, 36 sine theta cosine theta divided by 6 cosine theta, because that's going to be positive, d theta, and you can see that there's going to be a little bit of cancellation, so that equals the integral from 0 to pi over 6. Cosines will cancel, one of the 6's will cancel, of 6 sine theta d theta, which equals, well, integral of sine is cosine, so it's going to be 6 cosine theta, and we need to introduce a negative sign, all between 0 and pi over 6. Because we're doing a definite integral, we don't need to change our variable back into x. We could if we wanted to, because we know from our triangle that cosine theta, for example, would be root 3 over 2. Cosine of 30 degrees is root 3 over 2. When we have theta equals pi over 6, and we could go back through and actually change it back into x's and things, but we're not going to worry about that. Because it's definite, we can just substitute in our values just here. So that will be negative 6 cosine pi over 6 minus negative 6 cosine 0. And then we'll just figure that out. So cosine of pi over 6, as I just mentioned, is going to, I can use the same triangle, adjacent over hypotenuse, root 3 over 2. So it's going to be negative 6 times root 3 over 2 minus 6, and I guess we can simplify that slightly into being negative 3 root 3 minus 6. All right, so that's the end of that one, and that is a trig substitution. So just to recap, when you've got a trig substitution, one of your clues that you might want to use one is when you've got a square root of a number and an x squared. And you kind of just need to play with these two formulas to find the one that will give you the kind of cancellation you want. Here I basically wanted to turn a number minus a square into just a square, so that would undo the square root. So the 36 minus 36x squared turned into a single square, which meant the square root would go away. And if it was 36 plus x squared, for example, then I would have done x equals tan theta, and then the square root would have turned it into a sec, etc. Okay, we'll call it a day there, and we'll see you next time. See you later.